Okay, so we are working today with compound inequalities. Now this is opposed to the simple inequalities when I saw you last week. Oh, I forgot. Remind me in the last couple of minutes of class, I have your exams I need to return. I already got the recording going, so I'm going to move ahead. But remind me before we step out the last couple of minutes, and I'll make sure you get your exams back in your hands. Okay. So when I saw you last, we were talking about simple linear inequalities, okay, from 2.9. Simple, not meaning easy necessarily. Hopefully you're finding them easier the more you practice. But the idea of simple is that it has one inequality symbol. This is opposed to compound inequalities, which we have two inequality symbols. That's what we're looking at today. This comparison right here, this is from the notes last time, is one we'll come back to with compound inequalities. For right now, the comparison here is if you have a basic linear equation, you solve that linear equation, you get the solution. If you were to put it on a number line, it is just that number that will satisfy this equation, one solution, and we write it in set notation. And then comparing that with the inequalities, even with the same set, the same expressions, the same numbers, but with an inequality symbol instead of an equal sign, then what you're getting is not the solution, but rather the boundary point of the solution. It's where your solution begins or ends. Okay? Because we always write these, there's actually infinite solutions with inequalities. Everything up to that boundary point, or starting at that boundary point up to infinity. And so we use interval notation to show that smallest, comma, greatest, and that solution. You find it the same way with our strategies of general strategy of solving linear equations, linear inequalities. The only difference between solving them is that you do want to keep the x on the left with inequalities. And if you have a negative coefficient, the last step, a negative coefficient, then you flip the symbol. Otherwise, you're solving them basically the same way, but instead of a solution, you get your boundary point, which is either the end or the beginning of your solution. This same sort of comparison of the equal sign of equations to inequalities is going to be what we finish up with before the end of class with compound and absolute value inequalities. Okay, so I'll come back to that. What we're looking at today, 2.10 and then 2.12. So in 2.10 is compound inequalities, as opposed to simple inequalities. And the compound inequality, as I mentioned, it has two inequality symbols. It also means it's putting two simple inequalities together into one problem. So you can solve a simple inequality and you get your solution. But a compound inequality is saying I'm going to solve two simple inequalities, and the solution is not the solution just to one or the other, but the solution is how those two simple inequalities interact together. Now there's two different ways they can interact. One way they can interact is in the form of an intersection. And an intersection, and this will come back, this word uses the word and. And we'll come to that a little bit more. I'm going to set that aside for a second, but we're going to come to that. So these intersections mean this. You've got two sort of groups, two sets, but how they interact in an intersection is different from the second way, which is a union, which we're about to come to. But an intersection, let's say we've got one set. I'll say this circle is set A, and this set includes the numbers 1, 2, 3, 4, and 5. And then we have a second set, set B, which includes the numbers 3, 5, 7, and 9. Now if you're looking just at set A, that's 1, 2, 3, 4, 5. If you're looking at just at set B, that's 3, 5, 7, 9. In fact, we can write these, as opposed to this diagram, this overlapping circles, as set A is 1, 2, 3, 4, 5, using set notation, which just says we have a list of numbers. We're not talking about all the in-between numbers for this understanding, this defining of intersection. Set B consists of, these are called elements or members of the set. So set A has 5 elements or 5 members, and set B has 4 members or 4 elements. But these two sets interact in a certain way. Are there any members or elements that are the same for both? Yeah. We've got two elements in this case that are. That overlap is where set A and B intersect. Hence an intersection. Okay. Also often referred to as their overlap. Now the way we write that in math symbology is A intersects B. It's like an upside down U, no stem on the U, just the cup part. And that means A intersect B. So if just our set A is 1, 2, 3, 4, 5, and just our set B is 3, 5, 7, 9, if we want to say, well, what about the set A intersect B? That's its own set. In its set, the set of A intersect B includes what members? Just 3 and 5, which we can see visually here in the diagram, and we can also see looking at the members of each one, oh, they have 3 in common, and they also have 5 in common. Okay. So what they have in common is the intersection. Okay. Now for the intersection, so an intersection, compound inequality that involves an intersection is true, or let me put it this way, the solution is true for both of the simple inequalities. So we're about to, let me transition over to the inequalities here. So true for both of the simple inequalities. Okay. So an intersection in compound inequalities the intersection of compound inequalities means it gives you a solution that is true for both of the simple inequalities. You might have something that's true for one of them, and you might have something that's true for the other, but with an intersection, your solution of an intersection is only the thing that's true for both. 3 and 5 here are the only thing that's true for both of these sets. Therefore, their intersection is just 3 and 5. When we're looking at two inequalities, only what's true for both. So, for example, if you had x is less than or equal to 1, and x is greater than or equal to -3. So there's two simple inequalities. You just ignore the word and, it's like, oh, there's two problems. There's a simple inequality on the left and a simple inequality on the right. Now, they've both already been solved. There's nothing else to solve about them. Okay. If you were to write this in interval notation, the smallest value is -infinity, and then it goes up to and includes +1. Because x is less than or equal to 1. So anything less than 1, and we show that it also includes 1 with the bracket. So this one on its own, what's the smallest value that x could be in this simple inequality? -3, right. And -3 is included, and then it just keeps going up and up and up, anything towards as it approaches infinity. So these are all the possible values of x for this simple inequality, and these are all the possible values of x for this simple inequality. But together with the word and, we have a compound inequality. And so our solution set is not about the individual sets, but about how they interact as an intersection. We want to know the things that they have in common. Now, to visualize this, let's draw a working graph. And let's put these two different inequalities on one graph. So So I'm going to do that in two colors just to make it stand out. So this first simple inequality, x is less than or equal to 1. 1 is included, so I put that bracket right on 1 to show it's included. That's the boundary point of the solutions. And the solution to this inequality is everything that is less than or equal to 1. So the boundary point is 1, and the boundary point in this case is included, and the solution is everything less than that. Now let's put the solution, the graph of the solution of this one on the same graph. We'll do that one in a different color. I'll do green. And so we're starting at the boundary point of -3, and are we going to up or down the number line? Up. So we'll start at -3, so our bracket, and it is included, so we use a bracket, and it's pointing that way, and it is going up the number line. Now this little Venn diagram up here, we were talking about what's called discrete sets. Discrete meaning it's just a list of those numbers. It's just working with integers. We don't care about all the in-between numbers. We're just talking about there are 5 numbers. No, none of the fractions or decimals in between up here. Same thing with B. Okay? So, but the same idea of an intersection applies even when we're dealing with infinite rather than discrete. We're dealing with infinite sets where it's all those numbers in between numbers do count. It's still a matter, the intersection is still a matter of understanding where the overlap is or what they have in common. So x less than or equal to 1, this simple inequality, is all of these things are its solution, and the other one, x greater than or equal to -3, its solution is all of these things. But what do they have in common? Yeah, and everything in between those two numbers. So right here is the overlap. It is the intersection. It is what they have in common. This is what is true for both. Or, also, in math terms, it is the intersection. Now this, right here, if you put the two simple inequalities on one graph, this is what I could refer to as the working graph. This is not your final graph. Because you see on this working graph, you got all this stuff colored over here, and all of this stuff colored over here, and that helps you see, the working graph helps you see where they overlap, but only that overlap is the solution. This is not part of the solution, and this is not part of the solution. It's just where it's pink and green is the solution. So your working graph is not your final graph. It's just to help you visualize what the solution is. You put them both, simple ones, on one graph. You just note the word "and" means we're looking for the overlap. So your final graph for this is only the part that overlaps. So it includes -3, and it includes 1, and it's everything in between. The working graph shows the individual solutions of your two simple inequalities. Your solution to this problem is the intersection of these two simple inequalities, meaning it is the solution set of the compound inequality. And so that's the graph of it, and in interval notation is the least, comma, the greatest. Make sense? Questions? Problems? Now, compound inequalities, if they're intersections, can be written in what's called compact form. Okay. So I've seen that in working in, I believe I included a couple of these in 2.9, but just to be sure. So what this means, another way to look at this, what this means is that x, you see all the values of x are in this chunk of the number line. Okay? This is the solution to this compound inequality. And you can see all of the possible solutions, all of the possible x's are in between. X is between -3 and 1. So that means that our values of x must be greater than -3, and they must be less than -1. Another way to write this is with x in between. And notice how, even though this is a less than symbol here and that's a greater than symbol there, when we write this in compact form, we're going to be using two less thans, because one of them is read left to right and the other is read right to left. If we look at just this, what is this? Sorry, let me put it this way. What is the smaller value here? -3. So -3 is going to go on the left, and the larger value is. So we'll put this here. This is showing that x is in between these two numbers. Now we need the inequality symbols to complete that. If you look here at -3, notice, think of this like the jaws of something that wanting to eat the bigger thing. This is the jaws. The open jaws are, and I say this is a very directionally dyslexic person. This is the way, and some people are like, why are you telling me this like I'm, in elementary school? It's not meant to be insulting. I still have to think of it this way. And for those of you who are like, oh, that makes more sense, it's like, yeah, you know what I'm talking about. I always get these symbols and the directions of them mixed up. So I'm thinking that x, I always want to notice visually, see how it has the bigger gap there. So I make sure that's same here. So it's the bigger gap. This is like reading this, instead of from reading it from left to right, is reading it from right to left. X is greater than -3. The bigger the mouth is at the x, and the 3 is at the point. -3 is at the point. Okay, so I just flipped it over basically. Okay. And then x is less than or equal to -1. Okay. So when you write this in compact form, it's always two less than symbols, or less than or equal to, but it just puts x in the middle. So x is still read from left to right. X is greater than or equal to -3. It's just flipped over, read left to right, and this one is x is less than or equal to 1. But it's written as 1. This is a compact form. Intersection. Okay. So then this form, you don't need the word and, but it is there. Okay. So you have to write it in. So this one could be written either like this or like this. This is it with the word and this is it in compact form. Either way, it is an intersection. And this means that x is between the smaller and the greater value. In this case, x is between -3 and +1. So if you have, let's say, x is in between, let's say 0 and 5. Then you know you're dealing with an intersection. You're knowing you're dealing with a chunk of the number line. You just don't see the word and, but you don't even need a working graph for this one, because this is literally x is in between what's our smallest value, 0, and what's our largest value. And x is in between them. Now, the smaller value, 0, is it included in the solution? No. So we'll put a parenthesis there. What about the 5? Is it included? Yes. That's our rightmost value. It is included, so it gets a bracket. You might have 2 parentheses, 2 brackets, or in this case, a mix. And our solution, x, is in between those 2 boundary points. That's it. So it would be 0, 5. With the parenthesis and bracket to show what's included and what's not. And the word and is implied, because it's saying both of these things must be true. This must be true, and this must be true. The word and is implied, even though it's not written. Now, if you had a little more going on here, let's say 2x minus 10. you may have to do a little solving to get there. Here, I just gave you the final, this is the final answer, just like this one. There was nothing to solve here. You already have your basic solutions, even in compact form. Your x is all alone and naked in the middle, so there's nothing else to solve for x. Okay? There's nothing else to solve for x. X is just in between those two numbers. But if x is not alone in the middle, just like solving an equation, you have to solve it. You want x to be alone in the middle so you know what two numbers it's between. So we've got to get rid of the negative 10, and we've got to get rid of the 2. And we solve this just like we do any equation, inequality as well. You just have to get rid of everything that's bothering the x. It's just instead of being fair to one side or the other, you have to be fair to the left, middle, right. So first thing we want to get rid of is the 10. Right, anything added or subtracted. So we're going to add some 10 to cancel it out. Just make sure you add 10 on the far right and add 10 on the far left. Okay? You're just keeping the whole, this is like a 3-part scale. You just got to keep it all balanced. Okay? So we got positive 6 here. And finally, we're still solving for x, so we have to get rid of, in this case, it's a positive 2, so we don't have to flip any symbols. But we also have to divide that by 2 and divide that by 2. So now x is in between 3 is the smaller number, and the bigger number is 17 halves. Which is basically, I'll just go ahead and write, even though I say leave things as fractions, just so it's easier to visualize, 8.5 or 8.5. Even though you might have 2 positives, 2 negatives, or a mix, but the smaller number is always on the left and the bigger number is always on the right. And this means that both this is true, that x is greater than 3, read from right to left, and also x is less than 17 halves. Okay. And it'll always be the smallest one on the left and the greatest one on the right, and x is in between them. In this case, both of, or either or both or a mix of these included. Is the 3 included? What about the 17 halves? No. So 2 parentheses right on those boundary points. The parentheses tell you put them right on the boundary points, since the parentheses tell you they're not included. And you have a chunk of the number line. The value of x is everything in between. So your intersection might be written with the word and you'll see that overlap on the graph. Or in compact form, it might be written as x in between 2 values. Small, so x is greater than that smaller one, read right to left, and it's less than the bigger one, read left to right. And it's meaning it's in between. You got a chunk of the number line either way. Is that okay? Okay. So let's look at these possibilities. Make view 3. Make sure and scan that in. Okay. So we're going to solve 3 of these, and everything we just did right now, that chunk of the number line, is what you get most of the time. But out of these 3 examples, the thing I want you to do is to simplify the 2 simple inequalities and put them on a working graph and see how they interact. They might not interact exactly the way you're seeing there, what we just did, but remember, the answer is always the overlap. It is where they are in common. So we'll start with x plus 3 is greater than or equal to 4, and 5x minus 2 greater than or equal to 8. Now, you can't always write these in compact forms like the one I just showed. Here we've got x with a 3 added to it, and here we have x with a 2 subtracted from it and multiplied times 5. So we can't put x in the middle because different things are happening to x. So not every intersection can be written in compact form. Right? But it doesn't matter, we still know it's an intersection because of the word and. Solve each of these separately. Solve that one, and then solve that one. Treat them as 2 separate, simple inequalities. And then put them on a working graph. The 2 separate, simple inequality solutions on one graph. If you use colors, use 2 different colors. So you want to see 2 separate solutions on one graph to see what their compound solution is. And what? So there's one simple inequality with a boundary point of 7. So I start at 7 and I go up the number line, and note that 7 is included. And here's my second simple inequality. I'll put it on the same graph so I can see how they interact. 2 is my boundary point. I'm going up the number line, and 2 is included, so I start at 2 with a bracket and head up the number line.
7 or what?
Huh? What'd I do?
7 or what?
It's what?
Thank you.
I'm trying to like figure out this shit.
I'm so sorry. Yes, thank you. Feel free to actually shout out and stop me sooner on that one. I was trying to feel all this like in the room, but I'm getting a little daft this morning. All right. Greater than 1. All right. So, ignore that, thank you. And so 1 and 2. So yes, I'll do 0, 1, 2. Okay. So, greater than or equal to 1. And greater than or equal to 2. All right. All right, so in this case, unlike the first ones we looked at where they were going in opposite directions and had overlap in the middle, this one they're going in the same direction, but do they still have overlap? Yes. There's the overlap. That's the only part they have true together. Okay. So this is our working graph. Okay. Don't put this because this is not your graph. Your graph needs to be a nice clean graph that doesn't show 2 separate simple inequalities, but shows the one solution that is true for both of them. So for our solution of the compound inequality, where do we start? 2. We start with 2. Okay? Because all of this is part of our working graph because that was true for our first inequality, but it's not true for both, so it's not part of our actual solution. We start with where the overlap starts. Now that 2, is that included in both of these? Yes, it's included in both. Now if this were just x greater than 2, so that this were a parenthesis, then no, it wouldn't be included in both. It would have to be included, it would still be your boundary point, but unless it's included in both, depends on whether it has a bracket or parenthesis. That 2 is included not only in the pink one, which just overruns it, but it's also included in the green one, which because it has the or equal to. So we do start at 2, and we go up into infinity. That's the part that overlaps. That's true for both, and therefore that's our intersection. So the smallest value